So, not going to read this to you, but this is just an accompaniment to what you can read here with the tangent line approximations. Okay, so what we're going to be doing is taking a look at the line tangent to a curve, which we know how to figure it out, and then approximate. So we pick a nice value. So what's a nice x value? Close to 2.1? 2. So basically it's find a tangent line, or the line tangent to this function at x equal 2. First derivative, there's your slope of your tangent line. So your ordered pair is 2, 23. Set it up. Good. And then to approximate, you plug the original 2.1 in. Now we leave it this way, not simplified, not point slope intercept form, because this gives us a nicer calculation. We don't have to do this with a calculator. We're going to have to reach for a calculator, and that's the reason why you approximate. If we could use a calculator, heck, we just plug it in, done. Get the actual number, not an approximation. So this turns out to be 0.1 times 4.2 times 43 plus 23. Boom, done. Now, is this over and underestimate? Is this because this line isn't going to match? This line here isn't going to match this curve. It's not going to. Lines and curves don't match up. So how do we know? Second derivative. If it's positive, if the second derivative is positive at that nice value, as it is here, we have an underestimate. Now, before we start thinking about what's happening here, let's take a look at a figure. Here we go. What do you see? What do you see now? To me, it still looks like a line. How about now? Yep. How about now? Oh, wait a minute. I'm starting to see something. Maybe I need to keep backing. Wait, what's going on here? Notice when we were super close to this point, that curve, whatever that curve happened to be, was mirrored, modeled by that line. So this is what we call local linearity. And if we get close enough to a point, every curve, everything we've got, if we get really close, tight in, it's aligned. Now, this curve here happens to have, at this point, a second derivative that's positive. Notice how that line, the tangent line, if we go just a little bit, is less than the curve. So even if we're over here that you can't see unless we zoom out a little bit more, now you can start seeing that difference. That line is an underestimate. It doesn't matter if you go backward or forward. It's always going to be an underestimate underneath the curve with the positive second derivative. If we flip it around with a negative second derivative, we would then have an overestimate. That line would be above the curve. By the way, this is Wackel's tangent of x, and this is the tangent line at x equal pi over 4. Just for reference. Okay, so that's what we do that there. And then just there's the summary of that, and there's another example again. Give me a nice x value close to negative 0.9. Find the equation of the tangent line. That's why we did a lot. And then plug in negative 0.9. Boom, done. Second derivative. Yes, I went ahead and did actually I didn't use the quotient rule. I used negative. Oh yes, we have to use the quotient rule right now. Next week we'll get to use something different to find this derivative super quick. Okay. You don't have any of that in your practice, by the way. And then something else we use a lot of sometimes, that linearization. In other words, what's the model? The linear model, if we're super close to a point, well, it's the tangent line. That's all it is. It's what's the equation of that tangent line. So here, the linearization of g at x equal negative 1 is this tangent line. The linearization of this function f at x equal 2 is this. So we could model this function real close to 2 with that line. Real close. And that's all we're doing with this here. Because sometimes we can only approximate that way.